In this video, we'll be looking at a technique called implicit differentiation. And this is a technique that we use when we're trying to differentiate something which isn't a real function, but rather a relation between variables. So far, what we've been differentiating is just true functions of a variable, so one output for every input value. Sometimes we're interested in the instantaneous rates of change of what are called implicit functions, or things like the equation of a circle or an ellipse, where there's more than one output value for each input variable. Now, while it isn't possible in general to rearrange these implicit relationships into true functions, often we can still find information about how the variables change with respect to each other, using this implicit differentiation method. So how do we do it? Well, it's actually not that hard. Basically, the idea is, given you've got an implicit relationship between two variables, let's call them y and x like usual, we can find the derivative of y with respect to x by differentiating each part of the equation with respect to x, just like we normally would. Except every time it appears necessary to differentiate y with respect to x, we're just going to write y dash, or dy dx if you like. Now what you'll end up with is an equation which has maybe y's and x's in it, but it'll also have some dy dx's. The idea is then to just rearrange that and solve that resulting equation for y dash. So that's the final step here, step 3. Let's check out an example. We're given y squared minus 5 is equal to minus 2x squared. And we've got to find y dash, or dy dx. Now you can see here that this is one of those kind of equations where we can't really rearrange it to get y just as a function of x. If we tried, we'd get y squared is equal to minus 2x squared plus 5, and then we'd have the problem that we've actually got two possible values for y if we take the square root of both sides. So we have the situation where we've got an implicit relation rather than a true function. So we're going to use the implicit differentiation method shown on this slide here. So I've just copied that down to this slide so that we can follow along. The first step, differentiate each part of the equation with respect to x, just like we normally would. So I'm going to write this a little bit more explicitly than normal. I'm going to say differentiate both sides with respect to x, where the first side is y squared minus 5, and the other side, differentiate that with respect to x, the other side is minus 2x squared. Now this one's pretty easy, we've got rules for that. Over here we've got a situation where we've got a y squared, not sure what to do with that at the moment, but the derivative of minus 5, that's easy, that's just 0. So what we're going to have is the derivative of y squared with respect to x, not with respect to y, so we can't just write 2y. Over here on the right, we'll use our rules just to say that that's minus 4x. So what do we do with this one on the left side? Well, step 2 says each time it appears necessary to differentiate y, just write y dash. Well, yeah, that's true. So we're actually going to use a chain rule on this one. It's actually y squared, so the square function of the y function. So we're going to end up with 2 times y times the derivative of y by applying the chain rule. And that's still equal to minus 4x. Finally, at step 3, we've got to solve the result for y dash, or dy dx. So we're just going to rearrange things. So we end up with dy dx is equal to minus 4x on 2y. And cleaning that up a little, we can cancel some 2's, and we end up with minus 2x over y. So our derivative there, dy dx, is itself an implicit function, or an implicit relation, minus 2x over y. So there we've got our first example of implicit differentiation. Let's check out another one, a little bit more applied one. A particle is following a trajectory given by this equation, x cubed plus y cubed minus 9xy is equal to 0. And we want to find the slope of the tangent line to the path when x is equal to 2. Now in the application sense, that would be related to the velocity of the particle. Why don't you pause now and have a go at trying to do that one yourself by applying those 3 steps, differentiating with respect to x, using y dash or dy dx whenever necessary, and then rearranging. When you come back we can go through it together. Alright, so as in the last example, I'm going to differentiate both sides with respect to x. So I've just explicitly written that out so we can see what I'm doing. Coming down to the next line, derivative of a sum or difference is the sum or difference of the derivatives. So I can differentiate x cubed to get 3x squared. Y cubed, like on the previous example, I'm going to differentiate that kind of using the chain rule. So I'll get 3y squared and then the derivative of y itself we just leave as dy dx. Minus 9xy, that one's actually a product, right? It's minus 9x multiplied by a function of x, y. So I'm going to use the product rule there. So I'm going to pull the 9 out the front, and then I'm going to differentiate using the product rule. So I'll say it's y by the derivative of x, which is 1, plus x by the derivative of y, which is dy dx. So that's my product rule there. And the right hand side equals the derivative of 0, which is of course 0. So let's just clean that up a little bit. We're going to have 3x squared, leave that as it is, plus 3y squared dy dx. Busting these brackets open, we've got minus 9y and minus 9x dy dx is equal to 0. Now I'm just going to copy that and take it down to the next slide so that we can keep working on this, because we've got to rearrange now to solve for dy dx. Okay, there we go. So now I'm going to put all of the dy dx terms, keep them on the left, and take everything else over to the right hand side. So I've got 3y squared dy dx minus 9x dy dx, and that's going to be equal to 3x squared and minus 9y. Now I can factor out the common dy dx factor on the left. We got 3y squared minus 9x is equal to 3x squared minus 9y. And finally, just dividing both sides by 3y squared minus 9x, and I'm also going to cancel out a common factor of 3 as well. So we've got x squared minus 3y when I take the 3 factor here, and we're going to have y squared minus 3x. Okay, so we've got our derivative, or slope of the tangent line to our particle's trajectory at any point. The question asks us to specifically evaluate it at x equals 2 though. So just to clean this one right through to the end, dy dx at x equals 2, we're just going to substitute in. Okay, now this is going to be a little bit trickier than it looks, because we've actually got to figure out what y is going to be. So let's have a look at that. So what we actually need is the y value on our trajectory when x is equal to 2. Now this is a little bit tricky and beyond what we need to do really. So what I've gone over to is gone to Wolfram Alpha and asked it to plot the trajectory. So x cubed plus y cubed minus 9xy equals 0. And what that tells me is that when x is equal to 2, y is actually equal to this value here up at 4. Now that's the particular one that I'm interested in. There is another one down here, and you could figure it out there as well. But what I'm going to do is show you that when x is 2, y is equal to 4, and we'll look at figuring out what dy dx is going to be equal for those particular values. So what we're going to have is x equal to 2, so 2 squared, minus 3 by y being 4, y squared will be 4 squared, and minus 3 by 2. Now, if I evaluate this, I'm going to find that I get minus 8 over 10, or minus 4 and 5 if you like, or minus 0.8. Now this actually tells me that I must have made a mistake. Looking at our graph here, we can see that the tangent line is increasing from left to right. So I should have a positive gradient, or a positive derivative value, and I've got a negative. So let's have a look and see if we can find what the problem is. There must be a negative missing somewhere up here in the working. When we moved from the top line onto the second line, remember we tried to move things across to the right hand side. 3x squared went over to the right. Now what I've done here is I've actually accidentally done that exactly like that and just moved the whole things over to the right, whereas I should have had a minus 3x squared and a plus 9y, because when I moved things over I was actually subtracting them from both sides. That's going to follow throughout, and we're going to have the signs wrong on these and these, these and these. Then we should end up with our final result being correct at 4 and 5, or 0.8. And that makes a lot more sense. A positive gradient or slope of the tangent line that you can see there. So a good thing to check there is to make sure that you've got your signs right. And that's the kind of way you can go and backtrack and essentially debug your mathematics, if you like. If you want to now, you can actually go and figure out this other one as well, down here at the bottom. But I'm going to leave that to you as an exercise. So to summarise, we now know how to deal with relationships that are not true functions and how to figure out their derivatives and look at the rates of change of those kinds of variables. Implicit differentiation basically allows us to find those rates of change when we've got implicitly defined relationships.